A 2020 Boston University study found that your brain cells physically shrink by up to 60% during one specific phase of sleep. And that shrinking is the only time cerebrospinal fluid can rush in and flush out the toxic proteins linked to Alzheimer's disease. If you're over 50, you are almost certainly getting less of this sleep phase than you did at 30. In some cases, 80% less, and your brain is paying for it every single night. Most people believe sleep is one thing. You close your eyes, you drift off, you wake up. 8 hours? Good. 6 hours? Bad. That's the extent of what most of us were ever taught. But that understanding is dangerously incomplete. Your brain doesn't care how many hours you logged. It cares about what happened during those hours. Specifically, whether you entered a phase called slow wave sleep, also known as stage N3, also known as deep sleep. This is the phase where your brain waves drop to between 0.5 and 4.5 hertz. Slow, massive, rhythmic. And during this phase, and almost exclusively this phase, your brain activates a waste removal network that was only discovered in 2012. Before that year, scientists assumed the brain cleaned itself the same way the rest of your body does, through the lymphatic system. But here's the problem. Your brain doesn't have lymph vessels inside its tissue. For decades, nobody could explain how the brain removed metabolic waste. It was one of neuroscience's most embarrassing blind spots. Then Maiken Nedergaard's lab at the University of Rochester identified a completely new system, the glymphatic system, a network of channels that surrounds your blood vessels and uses cerebrospinal fluid to literally wash toxic proteins out of your brain tissue. And this system has a switch. It runs almost entirely during deep sleep. During waking hours, it's 90% shut down. That's not a metaphor. That's the measured reduction in mice and confirmed via fMRI in humans. So if you're not reaching deep sleep, if your brain can't generate those slow, powerful delta waves, your waste removal system is barely functioning. And the waste that builds up includes amyloid-beta and tau, the exact proteins that form the plaques and tangles of Alzheimer's disease. But the real question is how much deep sleep you're actually losing, and why your brain is quietly sabotaging its own cleaning system after 50. To understand what's happening to your sleep, you need to understand what deep sleep actually looks like inside your skull. During stage N3, large groups of neurons begin firing together in slow, synchronized waves. Picture a stadium where 80,000 people do the wave, that coordinated rolling motion where everyone rises and sits in unison. That's what your cortical neurons are doing during deep sleep. Depolarizing together, resting together, over and over in 20 to 30 second cycles. This coordinated activity does something extraordinary. It causes your brain cells to shrink. Not metaphorically, physically. The interstitial space, the gaps between your neurons, expands by as much as 60% during deep sleep compared to wakefulness. That expansion creates channels, and through those channels, cerebrospinal fluid floods in, carrying away the metabolic debris your neurons generated during the day. A 2019 study at Boston University, led by researcher Laura Lewis, used rapid fMRI imaging on sleeping human subjects and captured this in real time. They watched as large, slow-pulsing waves of cerebrospinal fluid surged through the brain every 20 seconds, precisely timed to the electrical slow waves of N3 sleep. During waking, CSF flow showed only small, faint pulses. During deep sleep, the flow was massive. The researchers called it a pulsatile washing machine. Your brain, quite literally, is pressure washing itself while you sleep. But here's where age enters the picture. A landmark study published in JAMA in 2000 by Eve Van Cauter and colleagues at the University of Chicago tracked 149 healthy men aged 16 to 83. They found that deep, slow-wave sleep declined from 18.9% of total sleep time in young adulthood, ages 16 to 25, to just 3.4% by midlife, ages 36 to 50. That's an 80% drop, and it happened mostly before age 50. By the time these men hit 60, they had almost no measurable slow-wave sleep left. Think about what that means for your glymphatic system. If 90% of brain waste clearance occurs during deep sleep, and your deep sleep is dropped by 80%, your brain's cleaning crew isn't working a full shift anymore. It's working a fraction of one. And the waste doesn't disappear. It accumulates, night after night, year after year. Researchers at UC Berkeley, led by Matthew Walker, published a review in the journal Neuron in 2017 that connected this directly to disease. The parts of the brain that deteriorate earliest as we age, Walker's team found, are the same regions that generate deep sleep. The prefrontal cortex, where slow oscillations originate, loses grey matter volume with age. That loss reduces your ability to produce the very brainwaves that trigger the cleaning process. It's a feedback loop. Less deep sleep means more waste. More waste means more neural damage. More damage means even less deep sleep. Some scientists dispute the exact magnitude of this cycle in humans, since much of the foundational glymphatic research was done in rodents. Depending on who you ask, the translation from mice to humans may overstate or understate the clearance rates. But the direction of the evidence is consistent, and it points to one conclusion that nobody argues with. Your deep sleep is declining, and your brain's ability to clean itself is declining with it. But this is only half the story. What happens at the molecular level, inside the walls of your brain's plumbing, is even more disturbing. The glymphatic system doesn't run on magic. It runs on water channels. Specifically, a protein called aquaporin-4, or AQP4 for short. These tiny molecular gates sit on the surface of star-shaped brain cells called astrocytes, cells that wrap around every blood vessel in your brain like a glove. The AQP4 channels are concentrated on the end feet of these astrocytes, right where the blood vessel meets the brain tissue. Their job is simple but critical. They allow cerebrospinal fluid to move from the space around your blood vessels into the deeper tissue of your brain, where it can pick up waste and carry it out. Think of it like a storm drain system. The AQP4 channels are the grates. When the grates are in the right position, properly polarized, as scientists say, fluid flows efficiently. Waste gets flushed. But when the grates get displaced or clogged or scattered across the wrong part of the cell, the whole system backs up. And that's exactly what happens as you age. A study published in the journal Aging Cell by researchers at the University of Rochester found that in aged mice, AQP4 channels migrated away from the astrocyte end feet toward the cell body. This mislocalization reduced cerebrospinal fluid flow and resulted in a 40% reduction in amyloid-beta clearance from the brain. In very old mice, glymphatic activity was reduced by 80 to 90% overall. If you've ever woken up at 3 a.m. with a brain that feels thick, foggy, heavy, like your thoughts are moving through wet concrete, this may be part of what's happening. Your glymphatic system attempted to run its cleaning cycle during your first bout of deep sleep, which typically occurs in the first 90 minutes of the night. But if that deep sleep was shallow, fragmented, or cut short by a bathroom trip, the system never fully engaged. And the AQP4 channels that were supposed to open the floodgates were already compromised by age. There's another factor that compounds this. During waking hours, your brain produces norepinephrine, a neurochemical that keeps you alert and responsive. Norepinephrine has a direct effect on your brain's extracellular space. It causes brain cells to swell slightly, squeezing the gaps between neurons shut. That's useful during the day because it keeps neural signaling tight and fast. But it also means the glymphatic channels are physically compressed. No flow, no cleaning. During deep sleep, norepinephrine levels drop dramatically. The locus ceruleus, a tiny brain region that produces most of your norepinephrine, goes quiet. That's the signal for brain cells to relax and shrink, opening up the interstitial highways for cerebrospinal fluid to flow. Nedergaard's team at Rochester confirmed this in a 2013 science paper. When they used norepinephrine blockers on awake mice, the mice's brains expanded their interstitial spaces and began glymphatic clearance, even while awake. The drug mimicked the deep sleep state. The research is still evolving on this, but the implication is striking. Your brain doesn't just need sleep. It needs a specific neurochemical state, low norepinephrine, expanded interstitial space, synchronized slow waves, that only occurs reliably during deep N3 sleep. And after 50, your brain has increasing difficulty reaching and sustaining that state. If this is making sense and you want the part about how to actually protect your deep sleep and possibly recover some of what you've lost, subscribe now, because that section is coming in a few minutes and it changes the way you think about your nighttime routine. But none of this matters if you don't understand what your body's sleeping position does to the speed of this entire process. What almost nobody talks about is that the position your body is in while you sleep changes how efficiently your brain drains waste, not by a small margin, by a significant one. In 2015, Helene Benveniste and her team at Stony Brook University published a study in the Journal of Neuroscience that used dynamic contrast MRI to track glymphatic flow in rodents sleeping in 3 positions: on their backs, supine; on their stomachs, prone; and on their sides, lateral. The results were unambiguous. Glymphatic transport, the movement of cerebrospinal fluid through the brain, and the clearance of amyloid-beta was most efficient in the lateral position, side sleeping, not back, not stomach, side. The proposed mechanisms involve gravity's effect on blood and cerebrospinal fluid movement through the skull, as well as the stretch and compression of key veins and nerves in each position. In the supine position, the jugular veins are partially compressed under the weight of the head, which may restrict venous drainage and slow the entire clearance loop. In the lateral position, drainage routes are optimized, and CSF flow encounters less resistance. Here's a detail that should make you pause. A separate study found that patients with dementia spent a significantly higher percentage of their sleep time in the supine position compared to healthy controls. The number of position changes per night was the same between groups, about 11 times per night, but the amount of time spent on the back was the risk factor, not how often you move, how long you stay flat. Read that again. Your sleeping position may be quietly influencing how much toxic protein your brain can remove each night, and you've probably never had a single conversation with your doctor about it. Now here's where this connects to everything we've discussed. If your deep sleep is already reduced because of age-related changes in your prefrontal cortex and slow-wave generation, and your AQP4 channels are already partially mislocalized, and your norepinephrine levels aren't dropping as low as they used to during sleep, adding a suboptimal sleeping position on top of all that creates a perfect storm of impaired clearance. Each factor alone might be manageable. Stacked together, they compound. There's one more piece to this that scientists are only beginning to understand. Nedergaard's most recent work, published in Science in 2025, proposes that during non-REM sleep, brain neuromodulators, norepinephrine, serotonin, dopamine, acetylcholine, synchronize into slow, coordinated oscillations that occur roughly once per minute. These synchronized rhythms drive vasomotion, which is the slow, rhythmic expansion and contraction of blood vessels independent of the heart's pumping. Vasomotion, in turn, is what physically pushes cerebrospinal fluid through the brain's glymphatic channels. Historians of neuroscience still argue whether the glymphatic system should be classified as true convective flow or enhanced diffusion. The debate is technical and ongoing, but what's not debated is the practical consequence. When these sleep-dependent rhythms are disrupted by chronic stress, cardiovascular disease, depression, medications like certain antidepressants, or simply aging, your brain's overnight cleaning capacity drops, and the proteins that should have been washed away stay behind. So the question becomes, if your body has this built-in mechanism, this extraordinary pressure washing system that runs on deep sleep, synchronized brainwaves, and proper body position, how do you protect it? How do you give it the best chance of working, especially after 50? Here is a protocol built on the current evidence. Not speculation, not trends, mechanisms. Step 1. Protect your first sleep cycle above all else. Your deepest slow-wave sleep occurs in the first 90 to 120 minutes of the night. This is when your glymphatic system is most active. The single most destructive thing you can do is delay your bedtime while still setting an early alarm. That compresses or eliminates your richest deep sleep window. Go to bed at the same time every night, within a 30-minute window, and prioritize those first 2 hours of sleep as sacred. Dr. Matthew Walker at UC Berkeley has emphasized repeatedly since his 2017 research review that consistency of sleep timing is more predictive of deep sleep quality than total sleep duration. Step 2. Raise your core body temperature before bed, then let it fall. A warm bath or shower 60 to 90 minutes before sleep increases peripheral blood flow and triggers a core temperature drop as your body radiates heat afterward. That drop is a physiological trigger for slow-wave sleep initiation. A study from the University of Texas at Austin found that water-based body warming 1 to 2 hours before bed improved sleep onset latency and increased slow-wave sleep duration in older adults. The temperature doesn't need to be extreme. Warm is enough. The drop is what matters. Step 3. Train your body to sleep laterally. Based on the 2015 Stony Brook research, side sleeping optimizes glymphatic clearance. If you naturally sleep on your back, use a body pillow or a positioning wedge to encourage lateral sleep. It may take 2 to 3 weeks to adapt. The evidence is preliminary and more human studies are needed. Some researchers dispute how directly the rodent findings translate, but the risk of trying is zero and the potential benefit is significant. Step 4. Exercise, specifically aerobic exercise, at least 150 minutes per week, but finish 3 or more hours before bedtime. A 2010 Northwestern University study of adults over 55 with insomnia found that a 16-week aerobic exercise program significantly increased slow-wave sleep duration, reduced nighttime awakenings, and improved self-reported sleep quality. Exercise promotes cardiovascular health, which in turn maintains the arterial pulsations that help drive cerebrospinal fluid through your brain's perivascular spaces. When those pulsations weaken, as they do with sedentary aging, glymphatic flow slows. Step 5. Consider your omega-3 intake. A study published in Nutritional Neuroscience found that omega-3 polyunsaturated fatty acids, particularly DHA from marine sources, protect AQP4 polarization on astrocyte end feet. In animal models, N3-PUFA supplementation maintained proper water channel positioning and increased glymphatic clearance speed. 2 to 3 servings of fatty fish per week, salmon, mackerel, sardines, or a quality fish oil supplement delivering at least 1,000 milligrams of combined EPA and DHA daily is the dosage range supported by current evidence. Step 6. Limit alcohol within 3 hours of sleep. While low doses of alcohol have shown complex effects on glymphatic function in animal models, alcohol is a well-documented suppressor of slow-wave sleep in humans, particularly in the second half of the night. It fragments your sleep architecture, reduces N3 time, and compromises the very neurochemical states your glymphatic system depends on. 1 glass of wine at dinner may be fine. A nightcap at 10 p.m. is working directly against your brain's cleaning cycle. If even one of these steps was new to you, hit like. It tells the algorithm to show this to more people who need it, and most people over 50 need it. There is something almost poetic about what your brain does while you sleep. Not romantic poetry, engineering poetry, precision, timing. A system that shrinks its own cells to create rivers of fluid that wash through 100 billion neurons every single night. A system that was invisible to science until 12 years ago. A system that depends on a sleep phase most people over 50 are quietly losing without ever being told. Nobody warned you that your deep sleep was disappearing. No annual physical measures it. No blood test tracks it. And yet the evidence now points to slow-wave sleep as one of the most significant modifiable risk factors for cognitive decline in the second half of life. The research from Rochester, from UC Berkeley, from Stony Brook, from Copenhagen, it all converges on the same finding. Your brain has a cleaning system. That system runs on deep sleep. And deep sleep is the one thing aging takes from you first. But it is not gone permanently. The protocol exists. The evidence exists. The tools, exercise, temperature manipulation, sleep positioning, nutritional support, timing discipline are available right now. They cost nothing. They require no prescription. I want to hear from you. Drop a comment below. What was the one thing in this video you wish you'd known 10 years ago? Was it the AQP4 channels? The sleeping position data? The 80% decline in deep sleep by midlife? I read every comment, and your answers shape what I research next. I bet most of you have noticed your sleep changing over the years. Waking up earlier, sleeping lighter, feeling less restored, but never connected it to what was happening inside your skull. Now you know. Your brain doesn't stop cleaning. It stops being given the chance. Share this with someone who needs it. A spouse, a sibling, a friend who complains they don't sleep like they used to. They're right, they don't. And now there's a reason and a response. If you haven't subscribed yet, you should. What's coming next week is something I've been researching for months. Your sleep is not a luxury. It is your brain's only maintenance window. Keep it open.